Tonight's speaker, Dr. Jerry X. Mitrovica, joined the Harvard Department of Earth and Planetary Sciences in 2009 as professor of geophysics. He received his bachelor's, master's, and doctoral degrees from the University of Toronto. He left for a while and then returned and spent 16 years on the faculty there, eventually serving as the director and fellow of the Earth Systems Evolution Program of the Canadian Institute for Advanced Research. Professor Mitrovica studies the Earth's structure and evolution, and these theoretical geophysical studies turn out to have a lot of important implications for our understanding of climate and sea level changes. His work is at the forefront of current efforts to understand the relationship between sea level rise and the melting of ice sheets and glaciers. Among his many honors and awards, Dr. Mitrovica was named a Fellow of the American Geophysical Union in 2005 and a Fellow of the John Simon Guggenheim Memorial Foundation in 2007. He received the Rutherford Memorial Medal in Physics from the Royal Society of Canada and the European Geosciences Union's Augustus Love Medal. He uses geological markers of uplift in areas of Europe and North America that were once covered by ice or water to understand the long-term evolution of the Earth, including the distinct geometries of sea level change, leading the way to modern efforts to fingerprint the sources of global sea level rise. Tonight, Professor Mitrovica will draw on that extensive experience with a lecture entitled In Search of Lost Time, Ancient Eclipses, Roman Fish Tanks, and the Enigma of Global Sea Level Rise. I'm very pleased to introduce Dr. Jerry Mitrovica.
Thank you, Maggie. Thank you. It's a real honor to be here. It's my third time in the Falmouth Woods Hole area. I gave a talk at Woods Hole a couple of years ago, and I related a story about my first visit, which I thought I'd start the talk with, and that was as a science fair judge. Somebody asked me, a friend from MIT, I think, asked me to come down and be the judge at a science fair, so I did it, not knowing what I was getting myself into. I was in charge of looking at 10 kids. They were 8, 9-year-old kids, and the first thing I realized right away is that these children had an engineer in their family. Either their mother or father was a Ph.D. in engineering, because there's no possible way they could have built the contraptions themselves. But the kid that I ranked first, a little kid named Joey, who I hate to say must be now in his early 20s, Joey was my favorite right away because he obviously had made his own project himself. It was a sundial that he had made out of cardboard, and it was very poorly cut out, and it was poorly glued together. But Joey seemed to know what he was doing next to these people with Ph.D. level engineering projects, right? And so I asked Joey a few questions, and he seemed ready, and I ranked him first, and then I brought him up to the other judges, and we were going to ask him a bunch of questions. And I said, Joey, tell us about the sundial. And he told us about the sundial. And I said, okay, so can you use a sundial 24 hours a day, Joey? And remember, he's 8 years old, very self-assured for an 8-year-old, and he said, yes, you can. And I said, really, day and night, Joey, trying to lead him on, day and night? In the night, Joey? And he said, no, it has to be in the day. I said, good, and can you use it every day? And he said, yes, you can. I said, no, really, Joey, think every single day. And he said, yes. I said, even, Joey, when it's cloudy and it's raining and it's dark, every day. And he said, and he looked at me like I was a moron, and he said, no, of course not. It'll rain on it. It'll ruin it. It's made out of cardboard. So Joey must now be a graduate student somewhere. That's the kind of thinking we like to give. And the second, so I have been at Harvard for a year, enjoyed myself a great deal after my move from the Great White North, as many Americans put it. My niece, who lives in Brussels, I'm her godfather, asked me after I arrived, was there anything that summed up my trip from Toronto to Harvard? And I sent her through the cell phone the following picture, which I thought summed things up perfectly. This is outside a Chinese restaurant, of all things, in Cambridge, Massachusetts, where violators will be towed perfunctorily. And I told her that the message was that, yes, you need a dictionary to make your way around Harvard. Because actually, when I first saw this, I saw a Japanese couple with their dictionary trying to understand what perfunctorily meant. So I've really, other than really strange eccentricities like this, I've really enjoyed my time. So let's start, and I'll start with the image that isn't really central to my work, but it's certainly related to it. I'm not really a climate scientist, but much of my work has implications in climate. And if you're thinking about climate, it all boils down to this very obvious figure. There's nothing controversial about this figure. There's many controversial issues in climate, it seems, but there's nobody at any sort of mainstream level of knowledge that would disagree with this image. It's simply an image of carbon dioxide concentration in parts per million as a function of time of a million years. And my work centers, believe it or not out here at the present day where we're worried so much about climate, but through this oscillatory period here. This is the Ice Age. These are periods where ice sheets grew and diminished. Things like Cape Cod were formed from glacial moraines with a 100,000-year heartbeat. You see 100,000-year cycles here. And I studied climate and sea level in that period. That's where I started. And, of course, a lot of the research now is directed towards more modern issues, and the problem sits here staring you right in the face, that no time in the last million years did carbon concentrations increase above 300 parts per million. But since the revolution, we're now here observed at 400 million, and your level of pessimism, the lower emission scenario says that by the end of this century we'll get to double carbon concentrations than double pre-industrial carbon concentrations. And if you're a little bit more pessimistic, it's 3 times pre-industrial levels. Now, you've probably seen climate talks, perhaps in this series, and people will focus their energies on things like temperature, the effects on ocean acidification. All sorts of people are talking about all sorts of implications. Very troubling trend in carbon concentration. I'll be talking about sea level. So I use sea level as a very sensitive lens on the climate system, and I'll try to give you an understanding of why, to some extent, understanding where we're headed and the anomalous areas that we're going to enter, you need to look back a little. And if you look back, if you want to make people stand up and pay attention that the problem we're facing is a very significant one, you have to prove that it's anomalous. The only way you can prove that things like sea level that we're seeing today are anomalous, to have a slightly more broader viewpoint and understand what sea level did in the last few years. Okay? These are just images I've taken off the web. They're pictures of so-called tide gauges. Given geophysics these days, etc., these are remarkably low-tech devices. They're simply cylinders with a sort of ping-pong ball in the middle. And as the water goes up and down, the ping-pong ball goes up and down. And you measure sea level over very long periods of time. And it turns out in some places like Sweden, where sea level changes have been dramatic, people have been looking at sea level change for the last 300 years. So the gauges have been out there in all sorts of areas, like the Antarctic. This is in the South Pacific, Venice, where I love to travel. This in the northern tip of England. I'm not really sure what these arrows are. I think that's just a toilet or something. But the, data is downloaded off. If you want every single piece of data that's been collected at this globally distributed network of tide gauges, it takes you about 2 minutes. You get onto a specific website, you download it all. You too can look at the analysis of sea level in the last few hundred years. It's all publicly available. So we use tide gauge records because they give us a long time window, a few hundred years, relative to the time window that's given to us by satellite records, which are more like 10 or 20 years. They give us a nice record of what's happened to sea level in the 20th century. Here's just a picture showing the location of tide gauges. One of the biggest problems in tide gauge research is that there are far more tide gauges in the northern hemisphere than in the southern hemisphere, and that causes some technical problems that I probably won't talk to today, but that are a matter of sort of ongoing discussion. Excuse me, I'm on decongestant, so my mouth quickly. This is an idea of the global distribution of these records. Here's the data that you get out of them. From 1900 right to the year 2000, this is sea level in millimeters. And a trend. It's obvious, right? The trend is about 2.5 millimeters per year. So 1/10 of an inch per year. In a decade, sea level has rose per decade in the 20th century about an inch per decade, right? And that's an inexorable increase. It's just going up. There's very little debate, if any, on this issue. Depending on speed, you might get as low as 1.5. You might get as high as 2.5. But they roughly, they all fall within that range. Again, there's no controversy. In the 20th century, globally, average sea level rose by about a couple of millimeters per year. Okay? But here is where the skeptics come in. So I could stop there, but there are three issues that are always raised. When I give lectures, even in very academic settings, it's quite often that I'm asked questions related to one of these 3 points. One is, well, 2 millimeters isn't so bad. It's not anomalous. Sea level's actually been rising at that rate for thousands of years. That is a common question I get, right, or a common comment I face. The argument is prevalent. You see it even in letters to the editors of newspapers when there's an article about sea level. The argument is, what's the fuss? It's been happening for thousands of years, so it couldn't have been induced by anything we've done to our climate. The second is, this is a little bit more puzzling. The first is easy to show it's wrong, but the second, less easy. Sea level change actually varies dramatically from place to place. You don't see that when I show you a figure like this. This is a global average. But if you go to place, or this place, or this place, or this place, you're not going to get that average. It can vary quite significantly. And that's an issue, because the typical viewpoint is if you're melting polar ice sheets, it's like turning a tap on in a bathtub, the sea level will rise more or less uniformly. Maybe not exactly, but why is it that some places sea level is rising by 10 times other places? And in fact, there are places where sea level in the 20th century fell. So what is at play here? And that is a very, very prevalent comment that's used even today when we know how to get around it. And I'm going to show you what the explanation for that is. And finally, something that is becoming more and more common in my talks to various audiences, I hear the following comment. Well, okay, you've got us. It's 2 millimeters per year, but that's stable. It's not really going to go up anytime soon. And I'm going to show you, in fact, that it already has. So we've lost that battle. So let's go through each one of these, beginning with this issue that sea level has been rising, according to some people, for thousands of years at this high rate. This is a coral, an exposed coral in the equatorial Pacific in a place called an island. Down here, there's Australia. I was actually born in Melbourne, Australia here, so it was not so far from where I was born. These sorts of features are endemic to those areas. If you go to any of these South Sea islands, you'll commonly see beaches that are now 2 or 3 meters above sea level, or you'll see corals that are dead. The top of those corals is dated to about 5,000 years. The 5,000-year-old coral, it's now a couple of meters above sea level. They're endemic. You see them everywhere. Of course, there's life, right? But something caused a mild sea level drop, and this coral died. Now, I think this is a very simple way of retorting the argument that sea level's done for the last 100 years, for the last few thousand. Of course, we have to correct things. I'll get to that in a minute. But think about it. This is a 5,000-year-old coral. It's now 2 meters above sea level. So if you do quick math, and I try not to do quick math in front of hundreds of people because I get it wrong, so I did it before, 2 millimeters per year for 5,000 years is 10 meters. If it were true that sea level were rising by 2 millimeters per year, as it has been in the 20th century for the last 5,000 years, this coral would be 10 meters under sea level. And it is not 10 meters under sea level. So this is a very geological, if you will, explanation for why that argument is incorrect. It happens to be an explanation I I'm understanding. In fact, we even know why sea level has dropped by that meter or two over the last 5,000 years. And that turns out to be because, and this is somewhat esoteric, but we were in an ice age up till 5,000 years ago. And places like Canada, Hudson Bay in Canada, are still popping up And other places like the U.S. East Coast are coming down because of ice age effects. The fact is, the Earth is still adjusting in some ways to what was happening thousands of years ago. And those processes act to bring water away from the equator towards the north. They act to drop sea level here by just a fraction of a millimeter per year. So this is entirely explicable, right? But it's certainly true that they completely rule out the idea, so often repeated, that sea level is, in the 20th century, was doing what it had been doing for millennia. But let's get to other evidence, parts of the talk that the title of my talk. This is now archaeological evidence. I'm going to reference in particular a colleague of mine at Australian National University. There's even a picture of him, Kurt Lambeck. In science, you often think that what you're doing is the greatest thing that anybody could be doing. That's the nature of the game. You're excited by doing it, you run to work, etc. But every so often you're asked to review a paper and you think, I wish I did that. And this is the one time in my career I read a paper and thought, I should have done that. And so I'll give you a couple of overheads explaining what Kurt and his Italian colleagues did looking at Italian sea level. Now, the Romans, particularly wealthy Romans, used to build fish holding tanks. So if you were particularly wealthy, through a 100-year period where they were particularly extravagant with their wealth, perhaps signaling the downfall of Rome, they built fish tanks, holding tanks. So simply, fishermen would bring in the fish, you throw them in the holding tank, and when you wanted to eat them, you just pulled them out of the tanks, right? All along this Tyrrhenian Sea coast, and for a remarkably short period of time, only for about 120 years. I've seen them. Kurt recently gave a sort of joint lecture, and we were very near this area, in fact. And I went out to see them after the conference ended. Sorry? Cements. So this is, you'll see. In fact, they cemented, to use that word rather loosely, but often they simply carved the fish tank out of the bedrock. Okay? So let's see some examples. This is an example up. I won't give you the Italian names. This is actually Kurt Lambeck standing on one of these fish tanks. This is another fish tank more towards the south. You're just seeing the remnants. What's interesting about these is that these aren't exactly the high point of Italian archaeology. There's very little interest in these things. They're not protected in any way. You can walk up there and stand on them because nobody thinks you. They just seem to be, in this case, cemented pieces just carved right out. Okay? Built to very, very precise specifications. Without going into the detail here, of course, you can't make the fish tanks too high, right? Because you want water to continually mix in with the water in the holding tank. You don't make them too low, the fish will just go over, right? So you have to make them a precise level relative to high tide, and with a precise kind of engineering approach to it. There was, I'll read the next plot, but you can basically see here is the bedrock in a sense, 2 columns here, a third column across here, and you had, what even I know from my engineering background, the sluice gate with holes in it. Holes that obviously aren't too large. You don't want the fish going through there. And you just lift them up and down. Okay. And here are examples in both. These are actual examples of the fish tanks. Okay. This is a long discussion of build such fish tanks, but the main aspect of this that's important is that they are now known from looking at many of them when they were built. So on this side, we're going to be talking about when they were built. They were about 20 centimeters below the top of this sluice gate was 20 centimeters below high tide. Okay? You didn't want to play around with this. If you had an anomalous tide, all the fish would get out, right? So you built it at this very precise level. Low tide was down here, so the fact that the waters went up and down over this range essentially proves the fact that this mixing of water was tidally driven. As the tide went up, a lot of water came in. As the tide went out, it came out. So there was this constant refreshing of the water in the fish tank. The fish are in here, right? Well, this is a very interesting thing because Kurt realized in seeing these, I think on a holiday, that this serves a very useful scientific purpose, We can use satellites to tell us what sea level's been doing for the last 10 to 15 years in a very precise way. We can use tide gauges to tell us what sea level's been doing for the last 100 years. But there are very few data sets that tell us what sea level was doing over the last few thousand years. Kurt realized he had one, right? So what he did is he went to every single one of these that he could find all along this coast, and he measured the present elevation of these features relative to sea level. He knew at what level they were built, and by comparing those two, he actually had a remarkably precise measure of sea level change over the last few thousand years since these were built. When he did that, this is just present day. So most of these markers are now submerged a little bit under sea level. But by taking the average, so I don't want you to understand the details of this, but each one of these is a fish tank. He took the average. And what he realized is that on average, these fish tanks are about a meter under present-day sea level. Okay? Now, there's a problem again, and it's one that I have to admit that I'm continually going to skirt around in this talk, but that's the Ice Age. Just as the Ice Age is causing those exposed a little bit over the last few thousand years, the ongoing effects of the Ice Age is actually causing Italy, the sea level, to rise in this region by a fraction of a millimeter per year. The reason is, when the great ice sheets that covered Canada and the U.S. melted, all the water went into the Mediterranean, right? Not all of it, but a significant increase in the level of the Mediterranean, and that caused the crust in the Mediterranean to subside, which led to a sea level rise. When you take account of this very small effect, instead of having these fish tanks a meter under sea level, they basically are at sea level. So what this tells you is, and when we account for the thing that we know, which is the Ice Age effect, these fish tanks are pretty well at the same sea level that they were. Over the last 2,000 years, Kurt and his colleagues concluded, sea level has been doing nothing much at all. And this is now considered probably the single most important constraint on sea level over the last few thousand years. There's no way of getting around this, right? And there is no way of arguing around it. If, for example, let's think again about that 2 millimeters per year. If 2 millimeters per year of sea level rise was occurring over the last few thousand years, over the last 2,000 years, that adds up to 4 meters. These things would be 4 or 5 meters under present-day sea level. They're not. Sea level is, the 20th century sea level rise is anomalous. It was obvious from the corals. It's now doubly obvious. But now I'm going to talk to you a little bit about some even more, in particular, linked to archaeological evidence that owes much to a very important scientist we were just talking about at dinner, Walter Munk. But I'll try to give you a sense of what's here. Stevenson and Morrison, scientists with strong archaeological backgrounds, decided that they would do something quite interesting. They understood that a lot of ancient cultures tended to be very interested in predicting eclipses, right? They weren't predicting eclipses from science. Those astronomers really, and not to disparage, but they were astrologers. Most cultures thought of eclipses as some harbinger of some evil thing that was about to happen. So it was in their best interest to understand when to hide, right? And so a lot of effort went into these cultures, into trying to understand when the next eclipse would occur, and to measuring very accurately the time of occurrence of both lunar and solar eclipses, right? Here's some examples. I've just thrown them on. I had a discussion with him about this. This is Chinese, and this is called the clepsydra. What this is, it's out of focus, I'm sorry, but it's just like, what do you call those things with sand? Like an hourglass. But instead of sand, you use water. And you very carefully calibrate the dripping of water to measure time. And they had these very, very sophisticated contraptions. Time passage through the number of drips of water that filled a bucket at the bottom of that clepsydra, right? So time. This all boils down to time, right? And this is a Babylonian clay tablet which measures the occurrence of a particularly well-constrained eclipse. I should tell you I can read that, but I can't read Babylonian. Right. So I have to ask my sister, a student of the classic, to just give you a sense of what it was that Stevenson and Morrison came up with. Because what they came up with was really very beautiful measure of what the Earth's been doing over the last few thousand years. What they did is, they said, I'm going to look at whether it be Babylonian, Chinese, Arab, or Greek records of eclipses, where they tell us as precisely as those records are kept when that eclipse occurred. Now, I'm standing here today. I can, using my highfalutin computer, tell me when that eclipse should have occurred. Right? I can look at the present-day rotation rate of the Earth, go backwards in time, and say that eclipse should have occurred at exactly 6:23. And what those guys did is they measured the difference between when the eclipse occurred and when we would predict it that it occurred if the Earth's rotation was as it is today. I know that's a very subtle thing. And what they noticed was a remarkable systematic misfit as you went back in time, which tells you details, but without at all. The Earth's rotation is slowing with time. The Earth's rotation 1,000 years ago or 2,000 years ago was more rapid than it is today. There is a constant slowing. Right? If you had two clocks synchronized at this point, and you waited 2,000 years, one kept to the present-day rotation rate of the Earth, and one just did what the Earth did, would be 4 hours out of phase. So in 2,000 years, that slowing of the Earth, scientists say integrates, adds up, is a more colloquial term, to 4 hours. So if you predict it at one point, using present rotation rate, it adds 4 hours later. And you don't always see it. One of the things I've fluffed in my discussion of this is that sometimes you would not see an eclipse because it would be daylight or it would be nighttime, right? So all of these things, or the eclipse is seen not at this town but this town at some distance away. And by taking a look at these things, these are all individual eclipses, right? So that's the systematic trend. There's no way around that. There's no debate now from this work that the Earth's rate of rotation is in fact slowing with time. And why does it slow with time? In some sense, to geophysicists, this was not a particular surprise. We know that it's slowing with time. And as residents of this area, you should know why it's slowing with time, right? It's slowing with time because of those water waves crashing. As these, and this is a picture taken from Cape Cod, every time these crash, they dissipate a little energy, right? As they do this energy over and again, without missing a beat, those crashing water waves dissipate energy. And what happens is the Earth's rotation rate slows, right? It seems imperceptible, right? It is. 4 hours adding up over 2,000 years. But for those of us like myself who are interested in what the Earth's rotation was like 800 million years ago, turns out it was 16-hour day, not 24-hour day. So the day has changed. But we're working not over hundreds of millions of years, but over thousands, and those slowing of the day add up to 4 hours, right? And for those of you who remember first year or freshman physics, I'm going to go into a digression that is mind-boggling, because, and that is, how do we know how much dissipation has occurred? Now, for those of you who actually break out in hives when you think of the word physics, and just ignore me for a minute. As a physicist, you live with that. Whenever I see anybody, a doctor, a dentist, they say, what do you do? I say, I'm a physicist. Everything freezes up. And you realize that everybody has some problem in their deep, dark background that involves physics. So now I just mumble, right? But if the Earth's slowing down, there's something in physics called the conservation of angular momentum. If the Earth slows down, something has to be rotating a little bit faster. Do you know what it is? It's the moon. So if the Earth's slowing down, the moon has to be orbiting faster. And if something orbits faster, if you take a curve more and more quickly, what happens to your car? You slide outwards. So what happens to the moon? The moon is leaving the Earth. And it's doing so by about an inch per year. And how do we know that? Because there was a far-sighted Apollo scientist who said, when those Apollo astronauts go up to the moon, we should leave mirrors there. And that's what they did. And so now, to this day, we shoot signals up to those mirrors and measure their two-way travel, back and forth. And by doing that over and over and over again, we have a very accurate measure of how the moon is leaving the Earth. And from that, we have a very accurate measurement of how much energy is being dissipated by these. It's mind-boggling. Whenever I talk to my science, I use that as an example of Earth system science at its most dramatic, right? That some mirrors left 30 years ago, 40 years ago now, gosh, time is flying, by Apollo astronauts are still used to make these measurements. But here it is. We call this tidal dissipation. Here are those eclipses again. This is a couple of thousand years, and those eclipses tell us that we're slowing down, and it adds up to about 16,000 seconds or about 4 hours, right? Now, what if we use this information that we have about dissipation? What if we actually go into our computer and say, you know what? The moon is leaving the Earth by 2 centimeters per year. This must mean this for the moon's orbit. It must mean this for the Earth's rotation. And I predict what? You predict that shaded line. You pretty well fit, right? There's small misfits, but it doesn't matter. You fit. What's most remarkable about this, the most remarkable thing about this plot isn't the fit. It's just how well those ancient cultures measured eclipses, right? When these guys look back at the boards, it was much easier for them to get the day wrong. Imagine, this is 4 hours. So you don't know when you're deciphering this whether it's March 16th or March 15th, but you'll soon know. Because if you make a 24-hour mistake, that point goes up through the roof. So you can bring it down when you've made a day mistake. The typical errors here are things like minutes, seconds. It's absolutely remarkable. The moon is, and mirrors are one thing, but the level of accuracy of these measurements is another. Right? So, and its recession tells us that this is tidal dissipation. We say, great, we're scientists, we like data get fit by a model, so it's all tides. But that's a problem. And it's a problem that was pointed out by Walter Munk. Because he said, there's, various parts to this. But he understood, although he didn't write this down, that this might be a way of countering the view that sea level rise over the last 100 years has been going on for the last 2,000. Now, why is that? Think about this. I have to get you back into physics here. You have the Antarctic. Well, actually, I said Antarctic, but that's only because I was born in Australia, so the world looks that way to me. You have the Arctic and the Antarctic, right? If those things are melting, what happens? Water leaves those poles and goes to the ocean, right? So if water leaves the poles and goes to the ocean, what will it do to the Earth's rotation? It will slow it down. Think of the iconic image all first-year physics professors use of the figure skater. When he or she does this and moves his or her hands out, they slow down. When they do this, they speed up. In the same way, if you take ice and melt it and put it into the oceans, which are largely around the equator, you will slow the Earth down. So we understood this and we did a calculation. We said, okay, you have that sea level rise has happened. So I can say, okay, I can do a calculation. I can ask, if that were true, that 2 millimeters per year would be constantly slowing the Earth's rotation rate, right? And it would be doing that for 2,000 years. So if we took tidal dissipation and we added that melt to it, what would we get? We would get that. So there is no way that what we're seeing or what we saw in the 20th century was something that we saw for the last 2 millennia. There is no way. The corals say no. The Roman fish tanks say no. And even ancient eclipses measured by the Babylonians and the Chinese and the Greeks say no. There is simply no way. You have to accept it. And happily, even those who said couldn't be shown now largely accept it. Yes, what we saw was different from the last few thousand years. So then what did they do? Then they said, yeah, but now you have a problem. Because the sea level that you saw in the 20th century varies. Where I was born in Melbourne, it's actually very different from offshore here. Why is that? Why? Well, let me give you an example of tide gauge. A bunch of 26 or 27 sites at which those cylinders exist with the picture I told you about it. And they've been measuring sea level changes at least a minimum of 50 years, right? Don't worry about this. I neglected the thing. But you want to put these places. One thing you want to do is avoid cities, because you wouldn't want to put a tide gauge just on the Boston Harbor or on New York's harbor, because cities have this I'm trying to think of a word I can, but a thirst for water, unquenching, I think I was thinking of. Thirst, I think I just made that up too, right? For water. And as they pump water, cities subside, right? So this would not be a good place to look for these. You want to get them away from cities. And when you look at those, and there's all sorts, you get this pattern. So this is the sea level rise you measure. These are European tide gauges here, New Zealand, west coast of the United States, South America, east coast of the United States, etc. Even in this, that in some places sea level is going up over 2 millimeters per year. In other places it was going up less than a millimeter per year. It's all over the place. In fact, this was so analyzed for so long, people had names for certain things. All of these sites here, those are European sites. European sites in this literature always show less than the global average. And this had a word. It was right? And they didn't mean that in a geopolitical sense. They meant what in Europe, that sea level somehow, strangely, in the 20th century, was going up less than it was everywhere else. And what's causing all this scatter? And, typically, until just a few years ago, geophysicists sort of looked at this, held their breath, and just took an average. And they didn't know what was causing that scatter, right? But I'm going to show you that sometimes implicit assumptions in science are the worst. I read papers hundreds of times where they will assume this. I just since read that, but then read it again. And here's the implicit assumption. The implicit assumption is, if you have an ice sheet and you have sea level, you melt that ice sheet. Sea level rises like a bathtub, right? When you take that average, that's what you're thinking. You're thinking, I know, it should be even. It's not. I don't know why it isn't, but I'm going to just take the average. It's a bathtub. So I've been working in sea level research for 2 decades now. Or about, that would be 2 inches of sea level rise, right? I should measure my experience in inches of sea level rise. How sad, right? And what I'm about to show you is the most counterintuitive result I've ever come across, right? You won't even believe it, I bet. An hour from now, you'll say, I got to email that nut, right? But it's true, and there is no controversy to it. It's now completely accepted. And we don't even have to worry about Einstein. We just have to believe Newton was right? And that is that when an ice sheet melts, sea level does not rise uniformly. It's dramatically non-uniform. An ice sheet, just like the Earth, exerts a gravitational pull on water. So if you have an ice sheet here, you pull water towards it. That shouldn't be a surprise, particularly where you live. You see water go up and down every day because of the sun and the moon. It shouldn't be a surprise that an ice sheet, which is much closer than the sun and the moon, will drag water towards it. Of course, this is a wild exaggeration, otherwise the middle of the ocean would be exposed. But it drags it. What happens when an ice sheet melts? Yeah, you are dumping water. You are certainly dumping water into the ocean. If you added up all the water everywhere, there'd be more water. But the other thing is that you exert less of a gravitational pull on the water. Because when the ice sheet melts, water moves away. So this is highly exaggerated, right? But if it melts, this becomes this. It turns out that close to an ice sheet that melts, sea level falls. That's ridiculous, but it's true. If you were standing at the Antarctic ice sheet, and the West Antarctic, which I'll talk about later, has enough water to raise global sea levels 5 meters, and I told you, you're standing here, tomorrow all of that's going to collapse and go into the ocean. It turns out that water at your feet, the sea level will drop 100 meters. Right? So this is a very dramatic effect, and it becomes more and more dramatic the closer you get to the ice sheet. Sea level, it does not go uniformly. In fact, where is this hinge point? That's the next interesting thing. Where is it the sea level does nothing at all? Because in some places it falls, in some places it rises. That's important. How far away from the ice sheet is that? And people thought, before we wrote those papers, well, it's got to be really close. No, it doesn't. It's 2,000 kilometers from the ice sheet. Show you an image that is really strange until you look at it. Well, I'm going to just play a little computer game. I'm going to say, here's Greenland. I'm going to take enough ice off Greenland that if the bathtub was right, it would go up a meter everywhere. If it went up uniformly, it would go up a meter. What does it actually do? Well, it does this. What this blue region here is, the deep blue here, right, is the region where sea level falls. So if you had in Scotland, I was at a conference recently, I made a terrible mistake. I pointed to an ice sheet over Scotland, and I said, and the ice sheet over the northern tip of England. And yeah, that did not go well. I heard, and half the audience walked out. So I've learned not to say that. That is Scotland. But if you knew tomorrow the Greenland ice sheet was going to collapse, you had a friend in Scotland, you called them and said, it's going to collapse, you should be concerned. Well, they shouldn't, except in some general sense. The Greenland ice sheet's collapsed, right? Right? Because sea level will fall in Greenland, in Scotland. It will also fall in Newfoundland. And then it will rise. You pay the price somewhere. It rises by progressively greater amounts as you move away, right? So that if you're on the Tierra del Fuego, the northern or the southern tip of South America, sea level will actually rise by closer to 1.4 meters, 40% more than you thought. Now remember, this is exaggerated. It's on one of these projections that stretches out the poles. You're going to have a bullseye around Greenland where sea level will actually fall. Every ice sheet will produce its own gravity field. So each ice sheet will have a very distinct image in sea level if it melted, right? Now, I don't expect you to understand all these details, but here's the fingerprint I just showed you. The Antarctic would have its own fingerprint, and these mountain glaciers like Alaska and Patagonia, etc., would have their own image. So think about what this means, because I started this whole spiel to say, look, sea level goes up in different places by different amounts. When you understand this, you realize that's perfectly understandable, right? Sea level doesn't go up in the bathtub. Sea level goes up very non-uniformly, very non-uniformly, very non-uniformly. There was an article in the New York Times a year ago. A colleague of mine at Harvard sent me a clip, and I thought it was really quite interesting to see. The article was about Alaskan fishermen who were dismissing all this talk about climate change because sea level was falling, right? That's why. The Alaskan ice sheets are melting. The gravitational pull on the water is diminishing. Water is moving away. So instead of saying, oh, those idiots who are talking about global sea level rise, understand that global sea level rise is a very complex thing. So now we no longer get worried about this variability from place to place. We use it because we say, how do I explain this? I have to add up this much of Greenland fingerprint, this much of the Antarctic, this much of the ice, the glaciers. Can I get the variability? And yes, you can fit the variability that you see. That means that we sort of held our breath in not understanding by putting a straight line in it. That's something remarkable. It tells you that by making 4 or 5 very nice measures of sea level, you don't just have a measure of how much sea level is rising. You actually can tell by looking at where it's coming from. It all looks like water to you, but by looking at how it changes from place to place, you can actually say 50% of this came from the Antarctic, 30% came from Greenland, right? Instead of being scared, you need to embrace it, understand that the physics, yes, I hate to use the word, tells you something quite dramatic. So now let's look at this last one. This is the briefest of my sections. But this I hear more and more now, quite often, actually, in every venue. I was in a debate about climate recently, and I was speaking about this over dinner. I refuse now to participate in such. happens is I get up, and I'm talking about sea level, and there's one person there who's saying, no, we have nothing to do with it. And the audience gets the misconception that 50% of people believe it is, and 50% it isn't. And so those days are now over. And I advocated at dinner that scientists should stop participating in those debates. It's giving people the wrong impression, right? But I hear this over and over again. Don't worry, yeah, it's small, 2 millimeters per year. What's the harm, right? It's not going to be so bad. Forget the fact that as that 2 millimeters, this is just a symptom. There's other symptoms, right? Lots more storms, etc. But sea level in and of itself, that doesn't seem so bad, a couple of millimeters per year, right? Okay, the argument is hasn't gone up. So here's that record that I showed you. This is highly controversial. Some people don't know if this is true or not. That's pre-1930 it was less. But as I talked to you before, about 2 millimeters per year in the 20th century. Okay, has that changed? It has changed so much that it's surprised every single scientist I know working in sea level. Okay, and I'll show you why. Now we look at the high-tech world of sea level. Now we go to satellites. And these satellites are whizzing over our heads. They're sending down signals which bounce off the surface of the ocean, go back up, measured by the satellite. And slowly, we're getting an image, a map of how sea level is changing, not from these low-tech cylinders that have done such a beautiful job, but now from satellites. What happens when we see those satellites? We get trends like this. Okay, it's all going up, right? No. Now it's 3.5 millimeters per year. Okay? So when people say to me in these forums, well, so what, 2 millimeters per year, it's stable, it's constant. No, too late, it's already gone up. It's at least 50% larger now. Sea level rise currently is 50% larger than the 20th century average. Okay? So it is going up. Right? There it is. Okay? But let me show you how this caught even scientists on their heels. Right? You may have heard of the IPCC report. This is the Intergovernmental Panel on Climate Change. This is this wide-ranging group of scientists that have get together, and every 5 years, I always avoided participating. It's like this, is it a Woody Allen comment or a Groucho Marx comment? I don't want to belong to any group that would have me as a member. I stay away from large groups of people. But here's the IPCC projection of what sea level will do. So here's sea level, and this is the tide gauge data, and here's the projection of where it would get in about 90 years from now. This was published, a year and a half ago, something like that. And so everyone thought that's bad, particularly bad, because we've already reached the upper bound of that projection. So the satellite data show us we're not in this range somewhere. We're now exceeding the upper bound. So in 2 years since that publication, we've already reached the upper bound of the trend that we thought we'd be on in the 21st century. Right? That's a very sobering thought. There's another scientist, not particularly a sea level scientist, who's shown a projection of sea level this century, and many of us would have liked to have seen this projection appear in the IPCC, but it's a much more logical use of the what we call the paleo data. There's almost no doubt in my view now that by the end of the century, sea level will be about a meter higher than it is now. So sea level is increasing. It's now increased above 20th century averages, and it's got nowhere to go but up. Even if we do nothing more to our climate, even if we don't spew another part per million of carbon, the Earth still hasn't warmed up in response to the carbon that's in for another 1 to 2 degrees of warming just based on what's in there now. And that's going to lead to problems. And so let me end with a discussion of why I particularly think that's going to lead to problems. And that's in particular going to be a discussion of the Antarctic ice sheet. So, here are the poles. This is the Antarctic. The Antarctic is an interesting continent. There, you have actually a large mountain range that nobody ever talks about, called because it's mostly under ice, the Transantarctic Mountains. This side of the Antarctic is called the West. This side is East. Obviously, that's sort of ambiguous when you're right on the pole, but that's the nomenclature. The West is a particularly problematic area of the of the Antarctic ice sheet. scientists, not all, think this is relatively stable, but everybody's worried about this, right? And why are they worried about the West Antarctic? You'll hear it. Next time you'll open a newspaper and you'll hear it, pay attention when they discuss the Antarctic, and invariably they'll be specifically talking about the West. What is it about the West that makes it so susceptible to climate change? The reason is it sits in a hole. This West Antarctic, this is a map of topography under the ice sheet. So if I took the ice sheet off, these areas in blue show that the West Antarctic actually sits in the hole. If the ice sheet wasn't there, there'd be ocean there. There wouldn't be land, right? Okay? And that's a problem, right? For a variety of reasons. The most basic being that ice floats, right? We all know that. We've taken advantage of it in our lives umpteen times. Okay? What does that mean? It means if sea level rises a little bit, there's a real concern that this will bring parts of the West Antarctic off the bedrock, and water will get in underneath, right? And it's like Greco-Roman wrestling. Once you're off the mat, it's over for you, right? Once that ice sheet comes off the bedrock, it's finished. It will just break away, right? So, do we have evidence of this? Oh, yes. This is a figure from Al Gore's book, the only figure I use from that book, showing ice shelf lost. This ice shelf was lost in 89, 95, 2000, 2002. But let me tell you what a bit of I want to give you some jargon. You hear about ice shelves and ice sheets. What's the difference? Ice shelves are floating, right? They aren't stuck onto the bedrock. But they serve a very important purpose in polar ice sheets. Because what they do is they act like a girdle. They hold the main back, right? If those ice shelves disappear, as they've been doing, right, there's nothing holding these ice sheets back, and they'll just enter into the sea, right? So the glaciologists use the word buttress. They buttress the ice shelf. But that really means they girdle it. They like a big rope around the ice sheet, keeping it in. The minute it's gone, there's a lot less keeping that ice sheet stable. And so these are pictures you've probably seen now, but I want to remind you of, right? This is the Ross Ice Shelf in 2002. This is this area here, okay? This ice shelf, that was thought for a long time to be a problem, and sure enough, in 2002, in a matter of weeks, it just broke apart. Right? This was, not the first, but the last in a sequence of events. 2 weeks over that, right? The whole ice sheet broke up and went away, right? And that wasn't really a surprise because people were concerned about it. But then, a few years later, in fact, only about a couple of years ago, the Wilkins ice shelf, here on this side of the peninsula, it also broke up. And it broke up in 2 days, right? You often see these images, and you'll see them again, trust me, right? You see this image here of the ice, this pristine white turns a kind of blue, right? What's happening here, in a matter of a day, the ice sheet just started, and what you're seeing isn't the water. You're seeing the deep of the ice sheet. In fact, what's this? Well, that just collapsed a few years earlier, right? And so now there's very holding the ice sheet behind their back. And so when people saw this, and this isn't my research now, I'm interested in this because I look at the sea level implications of this. But I'll tell you, even scientists would see this and say, that's okay. Because you know what? We know that the edges of these ice sheets are warming and they're but we'll be okay because most climate models at the time said that although the edges are warming and collapsing, the interior is getting cold and it's growing. So they'll be in balance. It doesn't look like it because you're looking at these edges, but if we step back and look at the whole ice sheet, we're okay because it'll be growing. Until this paper was published. This was a paper showing temperatures over the West Antarctic, right, as measured, again, by satellite systems, right? This is shocking for scientists, all scientists, even myself, who thought the same way. I thought, well, it's not going to be as bad as that. The problem is, and I won't go into details, is that the entire West Antarctic, not just the edges, not just the peninsula, which, by the way, has experienced the largest temperature change on Earth over the last 50 years, this piece here, right? But also the interior of the West Antarctic. So there is concern now that this ice sheet is in a collapse or will soon begin to collapse. Now, on the positive side of that awful story is that it takes a long time to melt ice. You know, I'm from Toronto, you're from the Northeast here. You know that at the end of the winter in Toronto there can be this huge mound of ice and it sticks around forever. And the reason is it's white, it reflects sunlight, and it stays cool. So when I say the ice sheet will collapse, that's not to say that tomorrow it will go. But it is that the process will begin, and it can take several centuries to continue. It will not take 3 weeks for that entire ice sheet to melt away. Right? There's too much ice. The scientific term is albedo. It has too much reflectivity. But what will happen? So let's ask a final question. What will happen? This is papers that I wrote and my graduate student, Natalia Gomez, wrote, who came with me from Toronto. Natalia is a little bit like Joey in the sense that she came from a very atypical world. She was a very renowned ballet dancer in Canada and decided after 5 years. You can always tell when Natalia gives a talk, everyone stands up straighter because her posture is perfect. But when she's asked a question, she will... So we ask her questions because we all just want to see her do that, right? But she wrote a paper which is troubling, right? What happened, forget, these are just 2 parts of the same study, different color scheme. This is a paper that asks the question, what happens if the West Antarctic collapses? What will happen to global sea level if the entire ice sheet goes in the next few hundred years? And the answer was so strange, we wondered whether we would be seen to be doing something a bit shady, right? This red takes the place of the deep blue in the last photo, so I should have used the same color. But this is the zone in which sea level will fall. So if the West Antarctic collapses, sea level will fall in that red region, right? So if you happen to have property in Tierra del Fuego, you're fine. Sea level's not going to do anything there, despite the fact that you've lost this. Where will you see the worst sea level rise? Over North America. In fact, just off the coast of Washington, right? Which is, well, I shouldn't comment any further on that, right? But it also, and why is this? And I'll give you a very quick explanation for this. But if instead of the 5 meters of average, you'll see closer to 7 meters over North America. Why is that? Well, one of the reasons I talked to you about, water will move away from the Antarctic and move upwards because of the gravity effect I talked about. So you'll get hit hard here. But it turns out that there's 2 other reasons that Natalia uncovered, which were you just have to shake your head. One is, remember I told you that the Antarctic sits in a bowl. So people for a long time thought that's a good thing, because when the Antarctic melts, the bowl's going to hold water. So not all of it will go out in the ocean. What they forgot until Natalia is, there's a problem with that logic. When the ice leaves, the bowl will bounce up, right? And as that bowl rebounds, it will throw water out, right? And we get hit. But there's even another third effect, which I'm not going to expect you to understand, but it's another one of these things that makes you appreciate the fact that I sort of stayed focused when I was taught about rotation. And that is that if the West Antarctic melts, it turns out that the rotation pole of the Earth, now this is where I was cautioned, no technical talk, but I have to say this because it's just so weird. The rotation pole of the Earth will shift a half a kilometer. And that shift will throw water up here and down there. So we get a triple whammy here. Gravity kills us, this bowl coming up kills us, and the pole shifting kills us. So all 3 effects give us this triple whammy. So sea level, you might think it's only 5, but you're going to get an additional 2 meters, right? Which is about this much, a little bit taller than I am, of additional water. And that's going to be very significant in terms of hazard, right? So that's it. These three issues that I talked about, the skeptics, 2 millimeters per year, they argue, is not anomalous. It's been going on for thousands of years. That is not true. You can now go to any talk on sea level, and if they say that, huff at them. So show your contempt in any way that you like. The second is sea level changes dramatically from place to place. How can that be? The bathtub tells us that's not true. Wrong. It has to be the case because ice sheets have gravity or produce a gravitational field. And as they melt, sea level does all sorts of things. We turn this around to our benefit because we use the fact to tell us where, not only how much sea level is rising, but where it's coming from. And thirdly, this is the most common thing I hear today. 2 millimeters per year is small and won't change. It already has. So thank you very much.